Hello and welcome to another lecture on galactic foreground emission mechanisms as a part of the cosmological component separation course. This lecture will be focused on synchrotron emission. As always, let's refamiliarize ourselves with the microwave foreground gallery. In this lecture we'll be focused on the green synchrotron emission line, which is predominant for frequencies, the most powerful in the sky below frequencies of around 15 gigahertz and is predominant all the way up until about 70 gigahertz. Overview for this lecture, we'll first talk about the physics of the synchrotron emission and then we'll look at some data. As far as the physics of the synchrotron emission are concerned, we will be using Rybicki and Lightman's chapter 6 as a reference for this whole section. So let's first imagine a relativistic electron moving through a magnetic field. The equation of motion is given below. And since the magnetic field cannot do any work on the electron, we know that the change of this of gamma mc squared will not or is equal to 0, which gives us that the gamma d gamma dt is also equal to 0. So walking through this from our equation of motion, since we know that gamma does not change, we have the equation below. So we're really focused more on the change in velocity as a function of time, which we can break into the two components that parallel with the motion, with the magnetic field, and that perpendicular to the magnetic field. We see that there's no acceleration parallel to the magnetic field, so what we have is uniform circular motion around the magnetic field. And of course, as a visual aid, we will introduce this figure here to show the red is the electron path, where blue is the photons coming out the sides of this path as we wrap around the magnetic field. Of course, as we just saw, the change in velocity is given by this uniform circular motion, and the gyration frequency is omega is given by the product of by E and the magnetic field's magnitude over gamma mc. And the power emitted, therefore, is proportional to gamma to the fourth frequency squared. In the non-relativistic case, cyclotron radiation electric field is seen by an observer, varies by the gyration frequency with a very spectrum at that frequency. However, in the relativistic case, the relativistic beaming shortens the pulses by gamma to the third, which makes the frequency spectrum that we observe here much broader. Again, for useful figures to kind of help see the differences between the classical non-relativistic view on the left and then a relativistic electron on the right with a strong beaming effect. We can show that the power emitted at a frequency gamma is given by this equation here with f omega over omega c, where f is just some dimensionless function that we won't define right now, but we also see that omega c is given by this equation here. Now let's assume that the electrons have some power law energy distribution n gamma, which is proportional to gamma to the minus p, which means that our power is proportional to the integral over the gammas of this this dimensionless function f and gamma to the minus p. Now we'll use a change of variables to get to something a little bit more usable, and we'll find that p omega is proportional to omega to the minus p over 1, or minus 1 over 2, and then times this integral of f of x, then x to the power of p minus 3 over 2 dx. As long as the integration limits are wide enough, such that, for example, x1 equals 0, x2 is infinity, we can then approximate this integral as constant, which in the end just gives us that p omega is proportional to this term out front. Therefore, we would expect that the shape of the synchrotron SED depends only on the electron energy distribution. In other words, factors like the magnetic field strength can change the amplitude, but not shape the actual spectrum of the synchrotron emission here, which is very useful. frequency integrated polarization fraction over all frequencies of synchrotron emission can be given by this capital pi, which is p plus 1 over p plus 7/3. And then for p is roughly equal to 3, which is what we expect for the synchrotron emission and what we observe on the sky, we have capital pi of roughly 75%. We won't get into the gory details of actually how we derive this. If you're interested, please see Verbicki and Lightman. One of the difficulties with synchrotron radiation is that it is susceptible to Faraday rotation. So you can imagine a linearly polarized synchrotron radiation that's moving through us, moving towards us through a magnetized ISM, and any linearly polarized wave can be decomposed into two waves of equal and opposite circular polarization. And the dispersion relations for left and right-handed circularly polarized waves moving through a magnetized plasma are different. So we expect a phase shift to occur as the wave propagates through the plasma and polarizes the light. How the effect of this Faraday rotation is given by the equations above, but we're mostly concerned with the actual effects here. The effect is strongest at low frequencies and high electron densities, and below 5 gigahertz and in the galactic plane, this is a big problem. It's not so bad at high galactic latitudes and at tens of gigahertz, which is nice because that's where we have most of our data. As far as synchrotron data sets are concerned, we are at a bit of a lack in CMB science for large-scale synchrotron observations, specifically in polarization. We have a nice template, essentially, of synchrotron radiation at 408 megahertz, which is a full sky, intensity-only map of radio synchrotron emission. And we do have some polarized synchrotron data given by SPAS at 2.3 gigahertz, which is southern hemisphere only, which has intensity and polarization, and then you have CBAS at 5 gigahertz, which is currently ongoing. Northern data is supposedly out relatively soon. Southern taking of data for the southern hemisphere has been postponed due to the pandemic, but this has observations of both intensity and polarization. Additionally, we also have Quixote, which has data between 11 and 41 gigahertz in the northern hemisphere in intensity and polarization, though this data is proprietary at the moment. Spectral index variations, this power law electron density that we were talking about, this P, is given usually in CMB physics by the spectral index beta S, a beta synchrotron, and we have seen in many cases that the spectral index varies across the sky. It isn't constant. For example, Svalheim 2020 showed some significant variations from minus 3.1, which is what we expect on most of the sky, in some significant portions, as shown here, steeper in the northern galactic spur and a little bit steeper than from the mean along the galactic wings. Synchrotron-Dust Correlation, we see that the synchrotron and dust have the same are both influenced by the same galactic magnetic field, so the polarized emissions should be well correlated if we use that naive assumption. However, synchrotron emission depends on the field strength and on the distribution of cosmic ray electrons, while the dust emission is independent of the field strength and depends mostly on the distribution of gas, because that's where the dust lives. But there is still some correlation, specifically along the galactic plane. And looking at these actual correlations themselves, from the SPAS paper, we see that there are some small correlations as a function of multipole between dust and synchrotron emission, both in the E modes and in the B modes, though a bit less in the B modes. In summary, the spectral behavior of the synchrotron SED is more or less entirely dependent on the electron energy distribution, which we assume is a power law. The observational evidence for variations in the synchrotron spectral index, which is the power law factor for this electron energy distribution, is evident. We also have to concern ourselves with Faraday rotation for comparing observations at low frequencies, as it can change the intensity of polarization. And finally, dust and synchrotron emission are correlated, but it is at a low level, not as much as one may naively expect just from the galactic magnetic field argument. Thanks.